I'm back with the second half of working with hardware. The previous video was about peeking, or reading, hardware registers, and this video will cover poking, or writing to hardware registers. So I won't be covering CPU registers much in this video because the demonstrations wouldn't be that interesting. Poking at really low-level stuff like that either results in the system working as expected or crashing. But I'll show some examples of what sort of things that those are used for. On ARM systems, the interrupt controller is built into the CPU. For those that don't know, interrupts are a way for peripherals to notify the CPU that the CPU needs to do something. Like say a packet arrives at the networking device, it'll send an interrupt to the CPU. That'll cause the CPU to stop doing whatever it's doing, look up whatever device sent the interrupt, run whatever code is needed to handle what the device needs, and then clear things up and get back to doing what it was doing. So we can see here, this is called by trap to handle IRQ interrupts. This is for the IMX8 kernel. This is the chip used in the IMT or the MNT Reform laptop. So we can see here it does one of these little sys read functions. In the last video I covered how in 9Front this is used to generate the sort of ones and zeros needed to feed an instruction to the CPU to read a particular system register. So it's going to grab whatever the number of the device that sent the interrupt, run through and look up what the device wants to do, run that particular function for it. And then down here it will do a write, and it's going to write to this particular register the ID number of whatever through the interrupt. That's a common way to tell the interrupt that it has been processed and can clear. So we can look in the manual here. So this is the ARM manual, and here's that interrupt, or not the interrupt, the register, and it's the interrupt controller end of interrupt register 1. And it says right here, writes to this register or to inform the CPU interface that it has completed processing the specified group 1 interrupt. But on ARM processors, these sort of things will be used for handling interrupts and setting up some, virtual memory and a few other sort of little functions buried inside the ARM CPU. And now on to memory mapped I/O. The trick to this is to do the reads and writes to a specific memory address. Usually you make variables that are stored on the stack, or you can allocate memory on the heap, and you can make pointers to those addresses. But in our case, we are making pointers to specific addresses. So next we need to know what to write into those addresses to get the results we want, and hopefully the data sheets are clear on that, or we can find some other code to give us some clues. For my example here, I'm doing an I2C driver for the MT7688. I have a data sheet, but it seems to give duplicate registers for some of the same tasks and some vague information on when to use them. So like I have a data in and a data out register, along with another one just called master data. Looking at them, the data in and data out are a single byte, but the other data registers, there's 2 of them and they both hold 4 each. So I looked at how NetBSD and Linux did it, and since I was able to test the Linux code and see that it functioned, I went with the way that they talked to the I2C controller. The method NetBSD used went with these single byte registers, but they were also mentioning reading some bits here that don't show up on the data sheet, so I wasn't sure if it worked. And one of those was an acknowledgement bit that they were using that I can't find on the data sheet, and that's really important for the way 9Front uses the I2C bus. So while it is possible to just sort of blindly fire stuff down the bus without an acknowledgement, 9Front kind of expects those acknowledgements to come back for sort of a routine it does, probing the bus on when it's mounted. So I'm going to be using these sets of registers here for the data in and out. and mostly this register here to actually issue commands, get the acknowledgements, and so on. So 9Front already has a system in place for adding peripherals like this. So down at the bottom of my driver here, I have this particular function. And it's going to call these things. It's going to pass along some information. So it's going to have the name of the I2C bus that'll show up, a speed that's expected to run at, the location of this particular controller data structure, which can have various information. Mine doesn't really have much other than information on how to set up the clock speed. And then it's going to also expect a function for initializing, and that's done when the system is first mounting this I2C bus, and then a function that will be called for any time I/O needs to be done, so any reads or writes. So right off, it'll run this init function. We can see here it's doing some math to set up the clock to make sure that the I2C bus is running at the whatever speed we want to run at. There's a couple kind of default speeds that most systems expect. So I've tested at the 100 kilohertz, and it also runs at 400 kilohertz. So I actually now have it running at the 400 as you saw down below. But this is basically just going to call this reset function. And that's here. And here's my first two actual writes to the I2C device, or the controller for it. And for the writes, I'm doing it this way. I set up a little define here for these macros. So for a read, I pass it some value, which would be the value, which is the number for a register. So up here, the registers I need, I already entered in the values for those, and also some values for various bits I might want to flip. But for the read here, I pass an offset. It gets fed into this. This here is another sort of little macro that takes all this and also maps it onto the uncached kernel addresses. So we have the base address, which is the starting point of the I2C controller, and we'll add to that the offset. For writes, it's the same thing. I'm basically getting that actual pointer to that specific place in memory and telling the system that it's going to equal whatever value we pass to it. So we can see here for the writes, we're going to be writing this controller 0. We're setting it clock stretch, enable, and then the value from init here to feed into the clock divider. So here it is on the data sheet. Here's the field that'll hold a value for the clock divider. And then there's the bits down here for enabling and the clock stretching. Clock stretching is an issue that happens sometimes with some devices plugged into the I2C bus, where the device itself might hold the clock a little longer than it should. So this just allows it to play nice with devices that are being fast and loose with the clock. So you'll notice here the value I'm sending to that control 0. This is the value here. It's the whole thing, and it has pipes between them. So these are logical ORs. I'm assuming that I'm starting, my starting point is all zeros. When ORing that, a 0 and a 0 is still 0, but a 1 and a 0 results in a 1. So I'm basically stacking all these values up to get the string of 1s and 0s I want. And that corresponds with the on-off switches in the register, or the 1s and 0s need to give a value to the clock divider. That should make the register give me the results I want. So on to the I/O function. 9Front packages up the data to be sent in a form pretty much exactly as how it would go down the bus. So not all operating systems do this. Some may separate out the device address and the read-write bit, but 9Front combines all of this. So this first bit here is just parsing out the address for debugging purposes. If I wanted it to actually print out the address to the screen when I'm doing writes. So next here we'll see this little busy function. So that's up here. So the busy function is basically going to read the control 1 register. It's going to put that into buff. It's then going to mask out with this AND here, just the control 1 trigger bit. And if it equals 0, it'll leave. If it equals 1, it'll keep looping 1,000 times with a little delay to slow it down. If it makes it all the way through the loop and it still isn't set to 0, that means the bus has been busy the whole time, and it will force the bus to stop, exit out, or return a 1, and that'll let the system know that there was an error and to handle that. So yeah, here we're using this little AND sign, and this is the mask, and we're just masking for the single bit we're interested in. If you remember your logic operations, an AND has to be both 1 and 1 to equal 1. So the trigger bit has a value of 1 shifted over 0 spaces. So here it is. If we look at the data sheet, that's on control. Here it is. The trigger bit, that's it. So as we can see here, read 0 if the bus is idle. You can set it to 1 to start the interface doing something. And if it reads back as a 1, then the bus is busy. So you don't have to put in a shift 0 to you could just put a 1, but I do that just to make sure that I know that I really do want to shift it over 0 spaces and I didn't just forget. But anyway, where was I? Oh yeah, the busy thing. So yeah, what this is doing is it's taking whatever value is read, so all the little bits in that control 1 register. And then the AND here with the mask basically means that the first bit there, if it is a 1, this thing will come back as 1. If it's a 0, it'll come back as 0, and it's going to ignore all the other bits in that string of bits. And that it's so yeah, it's 32 potential 1s or 0s in that string there. And next in the I/O, so then we do start, and start's a function here. It takes some sort of 2 values, and I package these up because this gets called quite a bit. So start will always cause a trigger event, whatever extra thing we want to pass to it, which was the start bit, and then some bytes, which in this case is none. After that, we finally get down to the actual reads and writes. So we've checked to see if the bus is busy, and if it's not, we've told it that we want to start using it. And now it's on to that part. So since 9Front packages up the data with the address and the read-write bit already placed in the first packet, we'll just go straight to output. So no matter what, even if we're just doing a read from an I2C device, we're always going to broadcast an address down the bus first to let the device know that we want to talk to it and that we want to read from it. So the first packet will have the address value along with the read-write bit. So packet is, it's pointed to here. It's one of the things expected in this I/O function. So what we're going to do is get the total bytes expected out and put it in this little, my own little O delta value here. It's always going to like come up as at least 1 or 2 just for the address. So first thing we do is remember we had 8 bytes in that, in those output data blocks, those 2 registers. So it's 4 bytes per register. 2 times 4 is 8. I have a couple variables here to hold the data before we write it out. I'm going to make sure there's 0 because this loops through if there's multiple things to write. So I just wanted to make sure to clear them. I will then move into data from packets, whatever number of bytes are expected to be written out. So this checks to see if it's more than 8, we set it to 8. If it's less than 8, we set it to whatever the less than value is. And then we do our writes here. So this is getting written to master data 1 or 0 and master data 1. And it will then send another write to the start register. And that is... So that goes into this mode thing here. And we have several different options here. So we had the start, and that's what we did before. And now we're sending a write, so that's the value of it. So once the data has been placed in the registers, we go ahead and tell it to do that. We then go back and do the acknowledgement. So like I said, the acknowledgement bit's important because right away it's going to write every possible address down the bus. If there's no device with that address, no acknowledgement will come back. If there is, it will at least send back an acknowledgement. And that's checked here. So again, this one's going to take in some bytes expected. And an interesting thing on the registers for that one there is that when you tell the system how many bytes you're going to send, you put it in here, and it's basically a binary value. But if you check, always read the fine print here. It's a maximum of 8 bytes, because that's how many you can fill in both those two 32-bit registers. But it says if it's set to 0, that counts as 1 byte. Because if this was actually 8, the 8 would be in this this bit here, which isn't used. So if you do 8 minus 1, that would be 7, which is 1, 1, 1. But up here is the acknowledgement field. The acknowledgement field doesn't work as like a binary value. It works like tally marks. So if 1 byte goes through, gets acknowledged, it just is 1. If 2 does, both these will be 1. And 3, 4, all the way up to 8. So every time it gets acknowledgement, it just flips one of these over to a 1 up to 8. So having to do that, this isn't just a straightforward compare two binary numbers. I'm actually having to do some math to convert them both to tally marks effectively. But yeah, so I just have to read the value back out, shift it over from that 16 bits, mask it out, and then compare the two. If I get back a matching acknowledgement value for the bytes I sent, return 0. If not, there's some problem, I stop the bus and return a 1 to let it further handle the error. But on writes here, it'll basically, if I have more than 8, it'll go through. This I is the index for the packets, so that will get incremented. The amount of data I have left gets decremented and then comes back up and just goes through it all again. So now on to the right end of it. So the right end of it is basically the same thing, just kind of reversed. So I start off by seeing, do I have anything going out? And while that's true, it will do this. I then figure out if it's more than 8. If it is, I set it to just 8. Clear out my little data buffers here. An interesting thing about I2C is that on reads, it will do an acknowledgement between consecutive reads. But on the last one, there'll be no acknowledgement. At least that's how it should work. So what this is going to do is it's going to check if I'm sending the last byte or not. And if I am, it will do a no acknowledgement, and otherwise do a standard acknowledgement. So then I do a start, say, put in whether I'm doing the read with acknowledgement or read with no acknowledgement and the bytes I expect to read. Sends that command to my little function that programs that into the control1 register. It then reads the data registers and puts those into my little data buffers, and then does a mem move to put that into packet at whatever the index of my point in the packet array currently is. It then does the acknowledgement, unless of course I'm on the last read byte, and then it doesn't bother. And then again, increment the index and decrement the remaining data to be read. And then when it's done, it comes down here, tells the bus to stop, and then returns whatever number of bytes were read and written, which is what the further code in 9Front expects. All right, and now to do a little demonstration. So I have the router here running and a little nested Rio window. So this Rio is actually running on that little router board. You can see it in the inset on the screen there. So first I have to add the I2C device to my namespace. And now I can check it. And remember, it was called I2C1. So the first time I try to read this directory, it's going to run that that probing function. So this will actually take a second to respond back, because what it's going to do is it's going to send every possible device address down the bus, and if a response comes back, because there's a device there, it will then build a corresponding set of files for that device. So there they all are. As you can see in the little window here, there is an LCD, and then the other thing is a combination CO2 temperature sensor. I've demonstrated those in previous videos. But yeah, now that's already probed the bus, it sets a flag that's been probed, and so next time I go to read that directory, it just automatically pops up. So I'll use my little LCD file system that I wrote already. And you can see on the screen there that it blanked the screen, which means it's initialized. I'll then do one for the CO2 sensor. So that will place a couple directories in mount, one for the LCDFS and one for the SCD40. So I'll go ahead and start reading from those right now. That's the mount SCD40. And there's my current temperature and CO2 reading and relative humidity for this room. But I can also do, let's see, it's LCD thing. And there we go. And you can see on the screen there, or the little webcam, it's now going to every second update the time, and then every few seconds update the temperature and CO2 reading. So there it goes. So that's actually, my little driver works. I can now send I2C or read I2C devices and write to them from the MT7688. So now I'll go ahead and just go through some of the other drivers on 9Front to give some other examples of how reads and writes are done. So again, this is for the IMX8, which is an ARM chip for the MNT reform. Here's the Ethernet driver. So again, you'll see they'll set up, either enumerates or as defines some offsets, and then bits that might be flipped. And then if I go down here, there's some more. And here they did a very similar sort of thing where they did a read and write, except they did it to this regs. So if you go and you actually find one of their reads, or let's see it right here, you'll see it adds this controller. So in the controller the way they handled it in this one, in the controller structure here, there is a unsigned 32-bit integer pointer called regs. And if we look that up, yeah, here it is. So PNP is gets called when an Ethernet device is being set up. And we can see here that it's going to set regs to same sort of thing, similar to what I was doing in my I2C, except they're using virt.io, which would be the virtual address set for memory mapped I/O devices on ARM chip. And then this would be probably the base address for the Ethernet device on that particular chip. So they're going to set that regs to here, and then up here, whenever this is called, you'll add the controller. It's going to say the controller regs, and then put in an offset for the read. And then for the write, same sort of thing, except they're saying, hey, whatever's at that particular address, set the value there to that. And to see them in action, let's see, what we got? Something down here. Ah, here we go. So this is when the Ethernet device itself sends an interrupt. So it's going to read from the Ethernet device itself. This probably holds like what sort of interrupt there was. It'll check to see what the value, you'll read the value from that register, put it into E. It's going to then mask E several times. And if this is probably if there's a receive, if there's a transmit, or if there's something to do with the ME interface. So it'll handle it. And then write back, and same like I probably mentioned before, it'll write back that value, which will just clear that interrupt. So very similar way that I was handling it on mine. If we look over in PCs, this is stuff for Intel chips. Let's go with our Ethernet here. Where's the, here we go, Intel Ethernet. So this covers a lot of the Intel gigabit Ethernet interfaces. Again, same sort of thing. We got a lot of like addresses that can be used. Basically registers that you might, offsets you might want to read or write to. Let's see, they're going to have probably, yep, same sort of thing. So they call theirs CSR32R and CSR32W for read and write. Same sort of thing. So in this case, it's controller pointed to NIC. So that'll be the read. You put an offset in, or if you write, you put the offset in, and then it's going to say that that equals to a given value. So rather than regs on the last example, this one's using NIC, and same sort of thing, integer pointer called NIC. I'm sure that's probably also set in PNP. Or no, so, oh yeah. So this might be a little bit, won't go too much detail on this because I'd take an old video of it itself, but this is going to be, attached to a PCI, PCI Express interface. So, so yeah, down here it's going to say that NIC is equal to mem. So mem is, yeah, mem's particular to here. So what's mem set to? Mem, if mem equals nim, oh, here it is, yeah. So mem's going to call this vmap function. It's going to P, which is, points to a PCI device. Bar, that's a base address register of some size with a size. So yeah, that's how PCI maps to memory, and it's going to talk to some bit of PCI mapped memory to get mem and then set that as NIC, and then do reads and writes to some offset of that address there. And that's how it's going to set up and communicate with the Intel's gigabit Ethernet stuff. So you can find a lot of this sort of stuff laying around now that you have an idea of what to look for. So let's try HGA. This is the Intel audio chipset. It's pretty standard on most Intel devices. And same sort of thing. You can see they're doing some enumeration for various bits and offsets for things. And if we go down, there's some structures, and yep, same sort of thing. So they're doing little defines to do same sort of stuff. And yep, except this time it's calling it mem instead of nic or regs. But same principle. That's how basically everything does it. So hopefully that gives anyone some ideas on how to go ahead and start writing with hardware. Like I've mentioned before, if you want to do this, it's probably best to set up some diskless terminal that you can boot off the network with, and that way you don't have to worry about corrupting any hard drives or doing anything like that. And just reboot the machine and go ahead and play with these things and see if you can make a driver or get something working that you wanted. And as always, have fun.